Hello from the Forcetronics YouTube channel, and welcome to 2 ways to speed up ESP32 GPIO reads and writes in the Arduino IDE. And if you're an Arduino user, I'm sure you're familiar with the popular digitalWrite and digitalRead functions for controlling digital or GPIO pins. But if you're using an ESP32, there's actually multiple ways to control your GPIO pins, and they tend to be faster than the popular digitalWrite and digitalRead functions. So that's what we're going to look at in this video, and we're going to do some benchmark speed comparisons. Please check out Forcetronics collaboration company Anabit at anabit.co, where you can find open source ADC and DAC reference designs, as well as projects, tutorials. Anabit also has a YouTube channel. If you go to anabit.co and your email address, you can get updates whenever there's new products or new content. If you haven't already, please subscribe to the Forcetronics YouTube channel. And if you like what you see here, please hit the thumbs up. Let's get started. Okay, here's the agenda for this video. First, we're going to talk about why the easy-to-use digitalWrite and digitalRead functions are a little slow. Then we're going to do an introduction into two other methods that are ESP32 specific: direct register control and API functions. From there, we're going to look at these three different methods for writing to digital or GPIO pins implemented in code. Then we're going to do a speed comparison using an oscilloscope. Then we're going to do a code review for the reads, three different methods, and then we'll do a speed comparison there as well. And then for my Patreon subscribers only, I'm going to show some fast write and fast read functions that I made that allow you to use the direct register control method, which you'll see is going to be the fastest. And the functions are set up to handle various ESP32 variants without you having to change the code. Okay, let's talk about Arduino's digitalWrite. And so the idea is these functions are awesome because they're very easy to use and they're portable, meaning I can have code that uses digital reads and writes, and I can use it with an ESP32 based board, or I can use it with a board that has a microcontroller from Microchip, right? It doesn't matter. I don't have to change those functions because they're very portable. But because they're so portable and easy to use, that comes at a higher software cost. And the idea is when you use digitalWrite or digitalRead, you're actually calling several functions. There's conditional branches. There's arrays where you need to look up pins. You need to see if pins are valid. And then finally, you get to the level that's specific to the board you're using. And if it's an ESP32, then you're accessing what's known as the hardware abstraction layer, or the HAL. So you can see there's a lot of overhead that comes with making these functions so easy to use and portable. And that overhead leads to a lag in execution from when you call that function to when you see that change on the pin or when that read happens from the pin. You can see the benchmark that I have. A digitalWrite, for it to go from low to high or high to low when it's called, can take 400 to 1,000 nanoseconds per call. But there's other ways to control those pins that are ESP32 specific. And I'm going to talk about 2 ways. There's actually more than two. So the first one is from the ESP32 IDF, and ExpressIF or ESP32 has various APIs for various peripherals they have. They have an API specific, though, for GPIO and real-time clock GPIO pins. This API is fairly easy to use, and it's portable across different ESP32 variants, meaning you could take that same code, copy it, and paste it, or use it for another ESP32 variant, and you shouldn't have many issues. It's going to require a special header file, which I listed there, and you'll see it in the code. And then as an example, I give you an example of one of its functions from the API. And I'm not going to go over the whole API. I'll have a link for it in the video description if you want to check it out. But you can show the example function I have there is the GPIO set direction. So this is like the Arduino's pin mode function, right? You define a pin and you tell it whether it's an input or an output pin. And of course, we have other functions for writing the digital pins or reading them that we'll see in the code. But the API is portable, it's easy to use, but it's not as fast as the direct register approach. It's going to be faster than the digitalRead and digitalWrite approach, as we'll see in the benchmarking. And as a little bit of background, the reason I dove into this topic is because I was using an ESP32 to control an analog to digital converter, or an ADC, that I needed to sample at 2 megasamples per second. And it uses SPI communication to control it and read the data off of it. And to get the fastest speed out of that ADC, I needed the chip select pin for the SPI communication to be able to turn on and off, or high and low, very fast, because that basically set the ADC when it did a conversion and when I wanted to read data from it. And what I found was I was not able to get the ADC to operate at its fastest speed because of the speed of the digitalWrite function. So anyway, that's a little background of how I got here. And I ended up having to use the ESP32 direct register control or bare metal access because it was the fastest. To use this direct register approach, you need the two header files that I have listed, which once again will be in the sketch. I'm showing an example call, which is sort of based on a structure, setting a pin to a high. And the pin number you want to change is the variable, labeled as the word pin. And so we'll talk about that more in the example code. The pro of using the direct register access is it is the fastest way to change the state or read a GPIO pin for the ESP32. There's no other way that's faster. But it's not very portable because some of the different variants have different ways of doing it. Some of them have different pin numbers. So you've got to be aware of that when you use this method. Also, this is more complex to implement because you have to understand how the registers work, what bits you need to flip, things like that. So the example that I'm going to show is not applicable to all ESP32s, and that's for the direct register access approach. It's going to be applicable for the variants that I'm listing below. This method won't support things like the H2 or the C6 because they have slightly different register calls or methods. All right, let's take a look at the code. Okay, you can see the header calls I'm doing up here. So these first two are for the direct register control. This third one is for the API. I have this set up so I can use compiler directives to tell if I'm doing a write speed test or a read speed test. You can see it's set up for the read speed test right now. I have to use a ESP32 enum for setting the pin, which is required for the API function. So that's what I'm doing here. And I'm going to use pin 5. Of course, if you get this code, you could always change this to another pin. Here's where I set up the pins, and it depends what test I'm doing. For setting up the pins, I'm just using the standard Arduino calls. And you can see as an example, I put in the GPIO set direction function from the API if you wanted to use that instead. And then we get into the loop, and that's where we're doing our speed tests. So first I have the compiler directive for the write speed test, which we're going to go over real quick. And so here is the classic way, the digitalWrite. And so what I'm doing is I'm doing a high to low 3 times in a row for our benchmarking. Then we have the API method, right? So like I said, for the API, we have functions a lot like the digitalWrite. For the ESP32, they have the GPIO set level, right? So we call our pin, test pin, and we set it to a 1 or a high. And then we set it to a low 3 times, just like these functions. Then we get into our register access. You can see GPIO.out, right? So this is structure-based for calling these registers. And this one that ends with an S means set, and this one that ends with a C means clear. So set means set to 1, C means clear to 0. And so what's happening is this is a 32-bit register, so that's why you're seeing a 1 UL. UL stands for unsigned long or 32-bit unsigned integer. And my test pin is the enumeration, which is going to match the pin number, which is 5. So I'm shifting it 5 positions into this register to say, hey, set this pin to 1. And same thing here with the clear. Now you can see I also have some other register calls that are commented out. And that's because some ESP32 variants have more than 32 pins. And so they have a second register. You basically take the pin number that's above 32 and you subtract it by 32. And this gets the right pin number for setting a similar register, but not the same register. So that's something to be aware of, and it depends on the variant of ESP32 you're using because some ESP32 variants do not go above 32 pins. So you can already kind of see some of the complexity that comes along with this. And as I mentioned for my exclusive Patreon content, I'll go through a function where we kind of have a way to handle the different variants of ESP32s for doing these direct register calls. Okay, so here's the speed test for the write. All I'm doing is high to low 3 times for each method. So here's an oscilloscope capture of those writes, those 3 writes, high to low, high to low, high to low for each method. So you can see this is an oscilloscope screen capture. So we have time on the x-axis and amplitude on the y-axis. And you can see I labeled the 3 different pulses, and you can clearly see how fast some of them are, right? So the digitalWrite is going to be the slowest because it has to go through various software layers. Then we have the ESP32 API, which we can see is clearly faster. And then we have the direct register access method, which you can see is much faster. And we're going to see it's an order of magnitude faster than the digitalWrite method. So here I zoomed in on one of the high pulses for the digitalWrite function, and we can see that it's 536 nanoseconds. I'm measuring that with cursors from basically the rising edge to the falling edge, from where it reaches high to when it transitions to low. We can see that measurement here, 536 nanoseconds, and here. That aligns with what the estimated was, which was between 400 and 1,000. So we can see almost over a half a microsecond to make that change. Then we have the ESP32 API, and we can see that it's about half that. So we're going about twice as fast now for using the API call, because once again, the API call has to deal with the different variants, so it does have some conditional branching as well and some other software layers. But the one that doesn't have any layers and you're controlling the register directly is the direct register access method. And you can see that it is much faster. And as I mentioned before, it's over an order of magnitude faster than the digitalWrite method. And we can see it only takes 49.6 seconds, or nanoseconds, I should say, not seconds. Okay, let's look at the 3 digitalRead approaches. Okay, here we are back at the code, and we can see my compiler directive else statement if we're doing the read speed test. And here, I can't really use an instrument, so I'm going to use the timing functions in Arduino, the micros functions. Now, unfortunately, I wish they had a nanosecond timer. They don't, so I had to use this micros function, which is not going to give us a lot of resolution on the speed, but it'll give us enough to push the point home. So here I get a timer value. I do a read, and I'm going to do the direct register access method first, and I do a read 3 different times. Right, so we're doing 3 different reads just like we did 3 different writes. And so what we're doing here is this is another structure call to the register. For the in register, I'm shifting to the test pin I want to use, and then that result is being AND with a 1. So the idea is if in that register portion there's a 0, and if you AND it with a 1, you'll get a 0, and if there's a 1 and you AND it with a 1, you'll get a 1. Right, so that's going to give us our digital result, and I do that 3 different times. And then, of course, I'm showing in the comment out section, if you're using a pin higher than 32, how you would implement it. Then we get our timer value, and then I do the same thing for the API approach. And we're using, once again, easy to use functions, right? GPIO get level, right? So that's going to return a 1 or a 0, just like the digitalRead that I have down here. And we're doing the timers for each. Then I do some printouts on the serial monitor, right? So here's the test results. I print out the microsecond timer, and then I print out the result that was read. And so right now I have it set up so there's a 3.3 volt connection to the test pin, pin 5, and so we should see a 1 for each one of these reads. And so I have an ESP32 running with this code already in the read test, so we can kind of see some of the printouts. And I'll refresh the information. So it's printing out at about 2.5 seconds in the loop. So there we go. There's some results, and we'll see another one print out. There we go. So we can see the speed for the direct register in the API is coming in at 1 microsecond. Now, they are actually different. They're not the same, but because 1 microsecond is our lowest resolution, that's what we're seeing. Chances are the API is just below 1 microsecond, and the direct register read method is going to be, fairly below it. But we're just seeing 1 microsecond come in, and then for the digital read, we're seeing 2 microseconds, which is not that surprising, right? We would assume that it's going to take about the same time as a digitalWrite, which would be about 500 nanoseconds. So that would be, a little over 1.5 microseconds. So that's why we're seeing the 2. And we can see each method is returning a 1, which it should be. And we can see it's consistent as we go down, and it continues to print out. So there we go. There's a demo from showing how we can do faster writes and faster reads, digital reads and digital writes, using some of the lower level functions for the ESP32 and not using the Arduino digital read and digital write functions. Okay, that's it for 2 ways to speed up ESP32 GPIO reads and writes in the Arduino IDE. If there's any questions you have, or if there's anything you think I want to miss or a comment you want to add, use the comment section below. Check out anabit.co, and thank you for watching.